Hello, welcome to the lecture for section 10.2 Concavity and Points of Inflection for Math 1325 Calculus for Business and Social Science. Concavity. What is concavity? You might think of a spoon and how it's curved, and concavity actually refers to the direction of the curve. We call something concave up when the C points up. Okay, this is when you'd hold a spoon normally. Okay. Notice that the function, you can barely see them there, but you can see some tangent lines at these points on the yellow curve, on the yellow function. When I have concave up, the function curve, or the f of x, is above the tangent lines. Concave down is when the C points down, or if you turned your spoon over, for example. And this is when the function is below the tangent lines. Again, you can just barely make out the tangent lines, and they're just a little bit above the graph. Okay? So how do derivatives help? So notice for concave up, the slopes are always increasing. Well, that doesn't seem right? It seems like we're going down. But remember, we're talking about the slope. So what's happening here is that on the left side of the graph, the slope is steeper and it is negative, right? And as it starts to bottom out here, it says starts to flatten out. Remember, the steeper the slope, when it's negative, the more negative it will be. Or the steeper the slope a positive, the steeper it is, the more positive it will be. Well, the more negative a number it is, remember, technically, that's a smaller number. Think of a number line. Even as we go to larger negative numbers, like negative 20 is actually technically smaller than negative 10. And we know this even from our bank account, right? A negative 20 balance is much worse than a negative 10 balance. Okay? So notice that for concave up, the slope is always increasing. It's going from larger negative values to smaller negative values to 0, and then to positive values, to small positive values, and then as it gets steeper, larger negative values. So the derivative f of x, f prime x, is always increasing. Recall, if a function is increasing, this means its slope is positive. So what we can do for concavity is we take the derivative of the derivative, or the slope of the derivative, which is the second derivative of f of x. So if the second derivative is positive over an interval, the original function is concave up over that same interval. So to figure out if something is concave up, we take the second derivative of the original function, and if it's positive over that entire interval, in this case from a to b, then we say that the original function is concave up. We know that the curve is facing up, like a spoon ready to hold liquid in it. By similar logic, concave down slopes, or f prime x, are always decreasing. So if the second derivative is negative over an interval, then the original function is concave down over that same interval. And this is if your spoon would be spilling something or letting the coffee or whatever you have in it out. Concavity. It's a roller coaster, baby. Notice the sine curve, the sine curve graph to the right. This function moves back and forth between curves that are concave up and concave down. Notice there is a point on the curve where it changes from one to the other, from concave up to concave down. And actually on these, I believe it changes right at the x-intercept, because it's symmetrical around the x-axis. So here we go from concave down, now we're back to concave up, concave down, concave up, etc. The point where it goes from concave down to up, or from concave up to down, is called the point of inflection. And it occurs when the second derivative is equal to 0. So notice that as we move from concave down to concave up, we're moving from positive to negative or negative to positive. So at that point, it's actually going to be equal to 0. When we go from a positive number to a negative number, we have to cross 0. And vice versa. If we're moving from a negative number, say -2, to positive number, say +2, somewhere in between there, it has to be equal to 0. So let's find the points of inflection. Remember, this is where the second derivative equals 0, and the concavity of the graph for this function. And the concavity, if it's positive over an interval, it will be concave up. If it's negative, it will be concave down. So first, let's find the second derivative of this function. The first derivative is 2x cubed minus 3x squared, and the second derivative is 6x squared minus 6x. Remember, we find that by just taking the derivative of the derivative. Pretty straightforward. Next, we find the points of inflections by setting the second derivative equal to 0. Notice if we set this equal to 0 and we factor, there's a common factor here, 6x. If we factor that out, we get 6x times x minus 1. And remember, if two things are being multiplied, if they're factors, we set each factor equal to 0 and solve. And so we get 6x equals 0, or x equals 0, or x minus 1 equals 0, or x equals 1. I'm not going to go through those functions. Those are pretty basic algebra functions, and you should know how to do that. Remember, now we also need to find the y values. So we plug the 0 back into the original equation and find the y values on the original function. Again, on the original equation. It doesn't say it here, but you need to remember that when we're plugging those back in, we're talking about it relative to the original equation. All right? So now we want to figure out what's happening at these points of inflection. Are they going from positive to negative or negative to positive? And that will help us figure out if it's concave up or down. Now, I like to use a number line, and in fact, even in section 9.1, or excuse me, 10.1 that we just came through in the previous section, I think it's actually easier to look at the number line with the original critical values, and then look at what, plug in the equation, in this case the second derivative, and look at the table and look what's happening before and after that. If we do that, we can see that the second derivative is positive before 0, negative after 0, and positive after 1. So when it goes from positive to negative, notice this is always decreasing, so we have concave down. When we go from negative to positive, we have concave up. All right? So we have a concave up here. We're positive all the way through. That's not right, is it at all? That's kind of strange. So notice we actually have a, oh no we don't, what am I saying? This is, the curve is pointing up, so we do have concave up. My bad, sorry. Sometimes these are intuitive to me and I'm looking at it going up. Remember, up means the spoon is holding the coffee, and so if this was the spoon, it is definitely holding the coffee. And what I'm thinking about is the first derivative, which is negative here, but we don't care about that. Okay, the second derivative is positive here. This is where it gets a little confusing because we're thinking of two different things. Second derivative is positive up until 0. Then it turns over, and you can see it's hard to see in this graph because it's just a little tiny concave down. But when it goes from negative to positive, we know that that's increasing, and then it's positive again, so we have a concave up curve. All right. Let's look at a real-life example. The point of diminishing return. This is the point at which profit begins to slow. Okay? This occurs at any inflection point. The annual profit for a store in thousands of dollars is given by P of x equals negative 0.2x cubed plus 3x squared plus 6. Where x is the number of years past 2010, find the diminishing returns for the profit. Note that the point of diminishing returns occurs at an inflection point. These are the critical values of the second derivative. Remember, where the second derivative equals 0. So we're going to do a similar thing. We're going to find the second derivative. We're going to then set it equal to 0 or to find the critical values. In this case, it's a simple algebraic equation to solve. We get x equals 5, which is the critical value, and then we get the point of inflection, which is 556. Again, we plug this back into what? The original equation. Now let's interpret the results. In 2015, remember that the x value represents the number of years past 2010, so P of 5 represents 2015, because it's 5 years past 2010. As profits reach $56,000, profit growth will begin to slow. Again, remember the y value is in thousands of dollars, so as profits reach $56,000, profit growth will begin to slow. So all that means is, doesn't mean we're not making a profit. It just means the profits aren't growing as fast from that point forward. All right. Let's look at the graphs from the last slide. Okay. What these are all three graphs. The first graph is actually the profit function, P of x. And you can see a little bit, it's not really intuitive or apparent that it's moving from concave up to concave down. And so at this point, 556, what's actually happening is our tangent lines are moving from beneath the graph to above the graph, if we could see them drawn in there. And at 556, it's moving from concave up to concave down. All right. The second one is the graph of our derivative of the profit function. Again, these I think are a little bit harder to see, but notice that what we're doing here is we have a possibly a 0 there, but then it's a positive graph because the slope is all positive here. So we're moving, we're going positive, it's still positive, it's still positive, until someplace up here it looks like it's zeroing out, but you can't really see it. So although our slope is still positive, over here, notice that our derivative, which is the slope value, are all in positive numbers. We don't ever get back to 0. But as we go, as we hit around 556, it's starting to slow down. And so notice that's what's happening here is it's all still positive because it's all an increasing function, but it's starting to slow down. So the y values are actually dropping. As far as the slope goes, the slope is getting less and less steep. Okay? So notice here we have the second derivative. The third graph is of the second derivative. And what we have here is between 0 and 5, it's a positive number, which is it's above the x-axis from 0 to 5, which means it's a positive number, which means it's concave up. At 5, at x equals 5, notice we switch across, we have an x-intercept there, but then we're now in negative values for our second derivative. And remember, negative values simply mean that it's concave down. All right. So here's some reminders about all this we learned and how it all fits together. If the second derivative is positive, the original function is concave up. This is the spoon that holds whatever you're eating, maybe a scoop of ice cream. If the second derivative is negative, the original function is concave down, and a negative spoon means that your ice cream falls in your lap, and that's kind of sad. We can use this to test if an optima point, the point of maximum or minimum, is a maximum or minimum. Remember, if we have a concave up, then the value in the middle would be a minimum. We have concave down, notice this is kind of secondary test. We already know how to do this by evaluating the slope before and after. So this is just the second derivative test. Find the optimum points or the critical values where the derivative equals 0. Plug the x value into the second derivative to see if it's positive or negative. If the second derivative at that point is greater than 0, then the point is a maximum. If the second derivative at that point is negative, then the point is a maximum. Okay? So we did this before in the last section. We found the optimum points by setting f of x, the derivative of f of x equal to 0. And we're still doing that with the first derivative. This is just how you can use the second derivative to quickly find out if they are a maximum